Hi, I'm Wai-Meng Mark from Supermicro. Today, I'm going to talk about delivering AI using NVIDIA NGC. And we're going to talk about three aspects of it. One of them is how do you deliver AI faster using NGC, and why is that true? And then we're going to talk about two ways to scale NGC. One way is to aggregate multiple GPUs together to solve bigger GPU problems or bigger AI problems. And then the other way is to integrate the different systems into a coherent system with AI into your business. There is rapid adoption of deep learning AI. This is just an example. In 2018, the BERT model was invented, built on top of existing AI models, but it was a significant breakthrough because it's able to do better question and answer and other types of natural language processing using the common words and sentences that we use. Significant improvement. Just within a year, researchers have adopted the BERT model to specifically look not just into the common language, but look into biomedical research language to build a bio-BERT model that can then go into biomedical research and bioarchive and medRxiv and other types of biotechnology research areas to summarize the information. So now, this year, researchers can quickly find the right information on COVID-19 research so they can help resolve problems with the pandemic. Another improvement this year is ProTrans that just came out. It's combining BERT model and multiple other AI models running on 1,200 systems. And this time, these systems not just interpreting common language, but rather they turn the 24 amino acids into words, and then the protein sequence as the sentences. And they look at that whole sequence as a way to look at how to interpret protein structures. And by the way, when you look at the COVID-19 virus, the crown that have all the pointed stuff that makes it so easy to enter human cells are constructed of proteins. So being able to actually understand protein structures quickly using computers will really help researchers to get us out of the pandemic. So this is just an example of how fast deep learning AI has come. And within 2 years, a model was developed and is applied in different areas. And we just see it in BERT, but there are many other types of applications as well. So what's driving this rapid adoption? Certainly, one of the reasons is because the faster AI has been developed. The second reason is NVIDIA has looked at this whole situation with the AI advances and has developed an entire ecosystems to help us use all these AI technology in a coherent fashion. And this ecosystem is called NGC, and we'll talk about that. And that really makes it much faster for researchers and businesses to actually deploy AI. There are other advances as well that help this rapid adoption. It is the infrastructure advances. There's certainly faster hardware that comes, and we'll talk about some of that. But more importantly is how do you actually scale these AI systems? One way is to combine multiple GPUs, and together they can solve bigger AI training problems. And we'll talk about that. A second way is orchestrating all these containers that have been delivered through NGC into the business workflow so that now you can incorporate AI into your business workflow. And that's a different way to scale. We'll talk about that. And in addition, toward the end, we'll have Jay Lawrence talk about how to extend this into the edge. 3 key drivers for rapid development. First, we're going to talk about NVIDIA NGC and the certified NGC-ready systems. When you look at the AI model, it's in a simple way. It's fairly complex when you look at all the details, but in a simple way, there are 4 key elements to AI. One of them is the data. Data is the new oil. with the data, then you can model what's going on in the real world. And these are the models that have been developed in the last 10 years. They have CNN model like ResNet and VGG that looks at images and figure out whether it's a dog, a cat, or a flower. There are BERT models that look at sequences of languages, or GPT and other types of models that are available to understand sequences of data. These models are implemented today using frameworks over the Python language. They could be TensorFlow, could be PyTorch, different types of frameworks are available. And all these run on top of the systems with GPUs in them, because GPU can really accelerate the processing of this data. And it can be coordinated very well using Docker containers. Now, so 4 elements in AI: data, model, frameworks, systems, and software. What NVIDIA has done is combine the models and the frameworks in containerized, easy-to-use, deliverable containers that can be deployed anywhere. And they can be deployed on these systems that are certified. And that's what we're going to talk about. And this environment with the containers and the systems is what makes up the NGC ecosystem. And the customer, by using this ecosystem, can just put in the data, do the training, and then actually deploy the AI. So NGC, NVIDIA NGC makes the AI faster, simpler, and very scalable to deploy. It's faster because everything is in containers. It just runs. The neat thing about container is the software stack that's in the container are consistent. So you don't have to worry about getting the right library. The right libraries are there already. So they're compatible, and then they can run. When you get a container, it will run. And each containers are maintained by NVIDIA so that the latest model and frameworks are there. What's more, we'll talk about this later, is some of the models are pre-trained. So you have actually, a lot of the work has been done for you already for training. And when you need to do inference on the edge or in the data center, they can be optimized using TensorRT. So all these elements make NGC a lot faster, easier to deploy AI. It's simpler because there's ways to manage all the GPUs in the systems, and also the updates. There are regular updates on the containers and the frameworks. There's also a specific set of industry focus into medical, into retail, and other types of areas that really makes it easier for specific industries to deploy this AI. And on top of it, when you run NGC software on top of NGC-ready systems, NVIDIA supports it. So that if you have any questions, they can resolve the issue with a particular network running on top of a particular version of PyTorch or something, and you can be assured that you can quickly and simply resolve your issue. And all these can be scalable. Scalable in the 2 sense that we'll talk about later. Scalable in terms of connecting or having multiple GPUs together, using GPU Direct to scale that system to solve big problems. And also, you can deploy all these using containers. And Helm charts are available in combination with Kubernetes so that the container has descriptions of what they need to be done. So Kubernetes knows where to look for the container to deploy in that particular infrastructure. And GPU operators can be used to deploy AI onto the edge. So all those pieces are there to help us scale AI using NGC. In the industrial focus area, I'll just give brief examples. One of them is Clara. NVIDIA has developed Clara to really help the biomedical industry. So there are tools built in, pre-trained models built in, that it can look at CT scans and figure out whether a lung has a particular disease or something. All those networks that are available to help that particular part of the medical industry. There are other aspects of looking at identifying people wearing masks so that social distance can be deployed. And all those built in the cloud. And then many other pieces for the biomedical industry that's built in, along with understanding DNA and proteins and so on. A second aspect is another industry that NVIDIA spent a lot of time on is using deep stream, looking at video images and be able to use that for whether it's self-driving car or for retail or looking at smart cities. All that can be deployed from NGC and then many other areas as well in terms of the industrial solution. So NGC is delivered as an ecosystem. On the bottom are the hardware. And Supermicro makes many hardware, and they all certified to run NGC with GPUs in them. And then, of course, you need to run the operating system, and that's either Red Hat or Ubuntu specific versions. And there's a simple layer of software that NVIDIA provides that has the CUDA layer as well as the NVIDIA driver, along with CUDA X that supports the AI software, and the Docker environment. The environment, along with the operating system, can be preloaded onto the system from Supermicro. So they can be delivered to the customer with essentially a system ready to go. And then the only thing they have to do is download the container from the NGC registry, and the systems are ready to deploy AI. And all this stuff is supported. Supported for the hardware level, for the OS level, as well as the NGC software level using NGC support services. They can be deployed on the edge using T4s. They could be deployed in the micro data center as a stack of small rack in remote locations, or they could be deployed in the data center running really high performance data processing. All these systems are available today. And these today, and we'll be certifying more systems as the A100 systems are becoming available. And those with A100 will also be able to support NGC. So NGC systems can really help develop AI much faster. Those are individual systems. Now we're going to talk about how we scale them by aggregating GPUs to solve big problems and then orchestrating the multiple containers to deploy in workflows. First, let's talk about aggregating the GPUs to solve big problems. As we look at in the last 9 years, there are multiple AI models that have been developed. And each year, as there's a breakthrough coming out, there's a more robust, bigger model that's needed. And in fact, each model that comes out requires more compute power to solve. Example is GPT-2 from OpenAI, just came out in 2019. It's like 1.5 billion parameters, takes tens of petaflop days to run. And this year, GPT-3 was released, and it's 100 times as many parameters, 173 billion parameters. And that system requires thousands of petaflop days to run. So as new systems, new AI model come out, they require a lot more compute. Also, the models gets bigger, and the models require a lot more compute. This is an example of RACE board. RACE is a test system where they have 100,000 questions. These are high school English questions. And just simple English questions that experts have created. And they give this to high school students to see how proficient they are with English. And the best person who could do it achieve about 95% accuracy in the RACE leaderboard. And when this was released in 2017, the best AI model could only do 43%. But last year, in 2019, when the BERT model came out with 336 million parameters, it could, running on a 128 GPU system, it could achieve closer to 76% accuracy. And now this year, with the Megatron BERT model, with 3.9 billion parameters running on 512 GPU system. It can achieve close to human accuracy, 91%. Bigger model requires more compute. Newer model require more compute. So how do you get more compute? Well, you need to provide more compute in terms of the number of GPU cores or GPU CUDA cores that are available by adding more GPUs. And in addition, you also need more GPU memory because all the parameters in the model need to fit inside the GPU in order to take advantage of the GPU acceleration. In addition to the model parameters, you also need to fit the data, the batch data that's needed to do the training inside the GPU memory in order to do the right training fast. So with a single A100, you get 40 gigabytes of GPU memory and 6,900 GPU CUDA cores. And when you have 4 of them connected by NVLink, you get 4 times as much memory and 4 times as much GPU cores. And you can go to 8 using NVLink and NVSwitch, and you get 320 gigabytes of GPU memory and 55,000 GPU CUDA cores. But sometimes that's not enough inside a single system. So how do you get more? You do more by adding additional systems on a fast network, 200 gigabit network, maybe multiple 200 gigabit networks. Connecting all those together, you can get to 512 GPU A100s that can give you over 3.5 million GPU cores and 20 terabyte of memory by just having 64 of these systems networked together. So that's how you scale. And all the software is available. They just need to run on the right hardware. And we have those hardware. Now, the software stack consists of this. It has underlying, you need to be able to connect the GPUs together using NVLink, if you have NVLink and NVSwitch, or you use GPU direct over PCI Express. And then over the network, you use GPU RDMA and GPU storage to access the data. To actually allow for the multiprocessing programming to work, you need NICO from NVIDIA and the MPI stack. Now, all the AI software is written in Python, so to coordinate all that, you run Horvath on top using Python to then leverage all that system. So once the hardware is set up with the NGC stack, just run Horvath on top, and you can scale your system to have really big system to solve big AI training problems. This year, 2020, is a significant year. We have the A100 coming out. But more importantly, the systems are changing as well. They are doubling in performance in terms of I/O bandwidth. PCI Express is going from Gen 3 to Gen 4 in the data center. And by doing that, you double the bandwidth that's available. And while you're doubling NVMe, you also can double the NVMe storage. NVMe storage also is going from Gen 3 to Gen 4. So you have significant improvement in read and write to storage. At the same time, the network is changing from 100 gigabit to 200 gigabit. So you get twice the bandwidth that's available on the network as well. So this is available with all the new systems supporting A100. Now, you have the hardware. You also need to be able to access data. And the data need a parallel file system to really supply the data into these really fast GPU systems. And there are many of them, and Supermicro works with many of them, like Wicked.io and Accelero, BGFS, and Lustre file system. All those are available, making NVMe Fabric a lot faster to access for data, to access the data so that you can do AI training much faster. Putting it together, that's what you have, is you have a really fast gigabit Ethernet network, 200 gigabit network, connecting the A100 GPUs, or the GPUs that are in the servers, in a cluster. And then you have the storage with providing parallel access to the NVMe. The entire system runs really fast. And NGC containers runs on top of it, so you can do the right AI training for the right model. That's how you're going to scale GPUs to solve big problems. So we talk about how we're going to scale multiple GPUs over the network to solve big problems. Now we're going to talk about how we can take the containers that are available to do AI and integrating them into the AI or into the business workflow. So let's take a look at the AI workflow in a particular business. You start with collecting data. You might be at a store and looking at people coming in. You might be at a store and tracking your inventory that goes on, or a logistics depot looking at the packages that go through, or in a medical facility, you look at patient data. All that data needs to be collected, and they need to be stored in data lakes so that they can be accessed for training. In order to train, you don't just take the data that you collected, you have to clean them. You have to make sure you have the images are in the right sizes, that they are normalized, and then you can pass through into the training system. The training system could be involved or it could be simple. It depends on how you implement it. If you use transfer learning, it could be much faster. If it's not, you might involve a cluster of servers to do training. But once the models are trained, then you have to save the model into a registry that then the inference system later can then pull from to know which model you need. If you need to look at image recognition, you go to the model registry to look at image recognition. Or if you need to do recognizing mask, you want to find the mask model. Or you want to look at a CT scan, you look at a different model. Or you look at a recommendation system, you pull a different model, you go to the registry to get that information. And you deploy those into the inference systems. It could be in the data center because you're connecting the websites, you're working with customers directly, or it could be on the edge. All that can be deployed using this system. And you might want to look at the data, visualize it, or you might want to even run simulations, see what's going on. This is the workflow that goes on when you collect data and go through training inference. But the data changes every day. Every day you come into a store, there's a new customer or different people coming in. You have different inventory on the shelves. You go into a medical environment, there are different patients with different types of diseases that could happen. So you have to constantly keep up with these changing data. Every day there's new data. You have to collect them. You have to go through this process. So this process is an ongoing cycle. In order to run a viable business, you want to keep up with this ongoing cycle. So how do you keep up with that? Well, the good thing is NGC is delivering containers. So they can be orchestrated and managed using Kubernetes. And that's a proven way of managing lots of containers. And it just happens that there are proven Kubernetes solutions already from Canonical and from Red Hat that can be used to run NGC. And Supermicro actually have done a number of reference architecture on this as well. It consists of running the Kubernetes stacks, be able to have a back-end storage access to provide the robust, reliable data that's needed, and be able to connect with Helm chart servers to get the right containers, and use GPU operators to deploy it on the edge. Everything running with NGC containers. And all this is built on a really robust network topology. The network topology has three key planes. There's the data plane that keeps track of all the data so that the servers know where to get the data. In fact, there are multiple data planes because there's some data that is slow data. So when you need to go to the internet to access data, maybe a 10 gigabit network or 25 gigabit network is sufficient. But if you really need to do AI training, and you really need to access the NVMe fabric to do the training, then you need maybe a 100 gigabit or 200 gigabit network to do that. So that's a separate network. So there are multiple data planes that are set up to allow the server in the cluster to access that data. And then you need to manage all these number of servers. And there are two ways to manage those servers. Very important. One way is the out-of-band control plane. And this is going through the IPMI ports and running redfish, and we'll talk about that, to really automate the process of understanding what's going on with power, temperature, with the environment that the servers are running in. And these could even run when the operating system somehow has failed, so that it can keep up with that infrastructure and notify the administrator if there's some really major issue that comes up. Out-of-band network, very important. But more important is the in-band control plane. This is when you deploy Kubernetes. You have to know what the IP addresses are. You need to know which server has what module and what containers are running where. All that is done, managed through the in-band control plane. So 3 planes, network planes, are very important in delivering Kubernetes clusters. Data planes, and it could be multiple data planes, out-of-band control planes, and in-band control plane. Now, you have the network set up, you have the whole server cluster set up. If you manually control every single server, and you have tens or hundreds of servers, and they have to be updated, it's going to take a long time. And you might not be able to keep track, you might make a lot of errors. So you want to automate that entire process. And the good thing is, whether you run canonical Kubernetes or Red Hat OpenShift Kubernetes, both support automated mechanisms. You have Juju and Moz in canonical, along with other types of like Chef and other tools that you can use to automate the process of assigning IP addresses, of loading the operating environment, along with knowing which server is what node, and then all coordinated in an automated fashion, in a scripted fashion. Same thing with OpenShift. It uses Ansible playbooks. So you can actually deploy the cluster using what they call infrastructure as code. You just code your infrastructure in essentially a number of files, and the system will execute that automatically. And then it can help you keep track of what's going on. Automating the cluster, very important. That's how you can deploy NGC in a scalable fashion. There are also other concerns that are necessary. The servers needs to be able to secure and be protected from hackers. And one of the key ways to protect against hackers is you don't want unauthorized software to run in your system. And the servers that Supermicro makes has built-in TPM, which has encryption and all these capabilities built in. But the most important thing that has, along with root of trust, is it prevents unauthorized software from running in that system. So every piece of software that runs in each system is secure, is protected from hackers. Very important, especially when you have a cluster, hundreds of servers running. The other piece is what we talked about before, out-of-band management. Each server has its own IPMI port that talks to a control processor for the server, so that whether it's GPU or CPU and memory and disk they're running in the server can be monitored by this management processor called the BMC. The IPMI connects to that in a separate network so that you can control the server independent of what's going on with the GPUs and CPUs. And to actually automate that process too, so that you can script everything and you can control hundreds of servers using a piece of code is the redfish interface. Redfish interface built into the server, into the BMC, allows you to script everything. And then, so you can automate the out-of-band management as well. Very important pieces. Security using TPM and root of trust, and then be able to independently manage the servers and automate the process using redfish. So putting it all together, there are three pieces. Now, on the bottom, out-of-band control plane using redfish automation and security through TPM as well as root of trust. On top of that, you want to run the Kubernetes clusters and all the software. And that provides the in-band control plane for that cluster. And of course, the data plane is where you actually run the NGC software and the model data and everything that you need to run your business. Putting it together, that's how Kubernetes can be automated and delivering AI to your business. So this flow of collecting data, prepping the data, training data, and deployment and going through cycle essentially can be automated. Automated through all these mechanisms that we talk about with Kubernetes. And NGC runs on top of that. That's how you deliver and integrated AI into your business. So in summary, we talk about this rapid AI adoption, and especially the three areas. What NVIDIA has done with the NGC ecosystem so that you can develop AI faster, and then how you scale in two ways, using how do you scale those NGC systems in two ways? By aggregating all the GPUs together over a fast network with fast access to data to solve really big AI problems. And the second area is you can orchestrate the containers into different servers within the data center to integrate AI into your business using Kubernetes and automation that we talk about. This is how you can rapidly adopt AI into your business. As we move forward, in addition to the data center running AI, AI will be on the edge. Very important because you want quick response time of what's happening with a situation out in your remote site. Something happened, you don't want to wait for the data to come back to the data center to go back to the edge. You want the processing local to the edge. So edge computing for AI is going to be very important. And we have Jay Lawrence to talk about how Supermicro is deploying AI or deploying edge systems. Thank you.
Hello, everybody. My name is Jay Lawrence. I'm the General Manager for Technology Enablement at Supermicro. Thanks for joining. I'm going to spend some time today talking with you about 5G, some of the applications it's driving, and many of the new product developments we have here at Supermicro to help to support the 5G application. So really the question we all hear about is, what is 5G? We all see the advertisements on television for the new handsets and all the new features and which carrier has 5G, but what is it? It's not just as simple as a phone. It's actually a complete restructuring of the telecommunications infrastructure, and we'll talk to that. But let's look at some of the things that 5G delivers. If you look at the improvements in bandwidth, they're substantial. Old bandwidth in the 3 and 4G was good for texting and streaming videos and 5G is going to get down to the point where AI and AR and VR and all those other sorts of very bandwidth hungry applications will be available because of the 10 then 100x roll up that we're going to see in the bandwidth being delivered by the network. There's a latency component as well. Latency in curtain networks is measured in tens or sometimes hundreds of milliseconds. 5G, that goes all the way up to 1 millisecond, almost an unprecedented speed. 1 millisecond. To put it in perspective, it takes the human body about 120 milliseconds to react to a ball getting thrown at you. So 1 millisecond puts your device really in a pretty elite athlete's performance category. There are other key features in the 5G environment. Availability of the network being 5 nines. Most power grids aren't 5 nines. So this presents an extremely big challenge to anyone building one of these networks. Now, how do these networks get from 4G to 5G? Well, a lot of it's through disaggregation. And again, we'll come show you some cartoons and some pictures of this, but disaggregation is what it sounds like. It's taking the compute and the storage and the networking that was traditionally centralized in a central office and bringing that out to where the users are and putting that capability, putting the data closer to the user, because getting that data orchestrated closer to a user is one of the key ways of getting the latency, for example, to the point where it's in that 1 millisecond, since the distance of the bit to the person needing the bit is usually the largest component in any telecom transmission. So that's part of what 5G is. And then you look at what it enables. Wonderful things. We talk about self-driving or autonomous vehicles. An example where latency is at a premium. You need to get that information to that vehicle in a very robust network quite quickly. All these AI and IoT applications for warehouse automation or other design applications or training. Again, all powered by Supermicro compute and storage and networking tools that give network designers the flexibility to put all that together. So we have, as one example, a telemedicine network going on right now. It's basically a private 5G rollout using some of the devices we're going to talk about through this discussion. And it turns the medicine community on its head, because now we have all of this new capacity going out to rural America that, just before 5G was talked about, was not something that was reasonably and efficiently easy to do. So as you look at these changes, and you can see there's a slide that kind of looks cartoonish at what the 4G network topology looked like and what network still largely looks like. It's very much hierarchical. You've got your central office and then pretty much a straight line of distribution down to the user. And again, this network structure serves its purpose, but as we look forward to where 5G is going to take us, you get this new complexity. And the difference in the cartoons is meant to be representative of almost the chaos, and that chaos creates value and opportunity when you disaggregate and take the central office, break it down, and get all that additional compute, storage, and networking capability closer to the subscriber, closer to the user and the client of the data. And that starts to give us all of those features we talked about in terms of what is 5G. More compute, more bandwidth, more spectrum, more bandwidth. Data's closer, less latency, multiple paths, multiple routes, multiple appliances solving the bandwidth requirement. That equals diversity, and that gives you availability. So all of these things roll up into what is a very elegant, albeit looking chaotic, but a very elegant new structure in the 5G network. And Supermicro has put itself right at the heart of all of this. So let's just talk a bit about something that we've done that's brand new. We're very excited about it because it is one of a kind in the market, and that is our SYS 1029GQ. This is a 1U server. It's got 4 NVIDIA V100 or 100Ss in it, which provides just a significant amount of workload and processing capability. But most important is that we've taken this device and gotten it successfully through the NEBS Level 3 certification. Now, NEBS is not for the faint of heart. NEBS strains, it throws radiation, it looks at emissions, there's thermal stresses, there's shock and vibration, there's even a simulated earthquake, and they try to catch the device on fire. We've done that, and we're the first and only to do it to this point. And this is enabling in the market. When you look at those structures and those cartoons of what the network's looking like as it evolves, having this sort of edge compute capability cannot be underscored. To get this to the edge where developers are working on AR applications, where you have autonomous vehicles, where you have warehouse automation, where you have the need to get so much workload to the edge of the network, which is central to 5G, this is a device that's been hardened both to survive comfortably and safely in a central office, which there'll still be needs for, but at the edge in less governed facilities that are less regulated. So again, one of a kind, first of its kind of the market, and right now it's only one of its kind of market. So we look at this as being something that has tremendous takeaway that highlights the ingenuity and the focus that Supermicro has placed towards its 5G portfolio. So we're going to look at this in a broader scale as well, which is the rest of our product offering that we have optimized for telecom. And this is where we are now. We're always evolving this. So we look at everything from core right out to the edge. And if you look at the graphic that's up on the screen, you'll see that the 1029 is listed down in the lower right. It's near the core, but it doesn't have to be because of the fact that it's been through NEBS and that it's gone through the hardening that NEBS demonstrates that it can handle. If you go to the other extreme, though, in the upper side of this box, we've got a white IP65 enclosure that we can put servers in. And IP65 is another great way for getting this compute capability out to the edge. We've got a number of servers that can fit in this box. Those servers give us a lot of scale and flexibility for multiple expansion cards, so you can get FPGAs, GPUs, and the like right at the edge in an outdoor enclosure that doesn't even need a new data center. So like I mentioned in the example of remote telemedicine, this could put a tremendous amount of compute capability right at the edge where it's needed for latency, for all the analysis and all the software applications that you want to run in a telemedicine type application, and you don't even need to have a new data center or a central office to get there. Going around the horn, again, these are products that we've optimized for the telecom application. This is not our whole kit and caboodle. There's a lot more that we can do, and we're continuing to invest. But everything we're showing you here has some truths. One, there's flexibility and scale. Lots of expansion slots on all these devices. All of them promote DC power, which is important for our telecom customers, and every one of these devices has that capability. They all have been or are just about to wrap up going through NEBS Level 3 certification. So everything here will have that very important certification on it that even if you're not a Tier 1 telecom, maybe you're in government or just doing something else that is going to be demanding in its environment, and you want that good housekeeping seal of approval, all these products, all these devices possess that. So we also have a new product, our Hyper-E, which is in the upper right, that's coming out soon. But again, it will have all the NEBS support, DC, but also front I/O, which is important to some of our customers. So we've listened to what the market's been telling us as we've come up with this suite of solutions. And I do want to stress, whether it's the 1029 GQ, which is a one of its kind, anything else that's on here, or if you have a challenge that you don't see here, bring it to us. We'd like to help you solve that problem. So going around the horn again, one of the things I always like to say is what happened when I first told one of our customers about the 1029 GQ coming to market, which is, this is fantastic because now we can do things today we couldn't have contemplated yesterday. So as Supermicro looks at this space, we want to be leading in it. And we have made the investment both in the lab time to do NEBS, the product development time to get these new products to market. We've listened to our customers and continue to listen to our customers and want you to be bringing us challenges, because just because you may not see it today doesn't mean that we can't put together a winning solution with you and get it through the certifications to give the kind of workloads and other capabilities that you'll have in concert with you. So we want to encourage that. Again, as we look through everything that we've done to date, it's a very impressive portfolio that services and is targeted to this new 5G environment, and we're looking to continue to expand it and look forward to doing that with you. Thank you, and that's all.